Welcome back to day 2 of the ROS short course. Get the lights. If the sun is blasting in too much, feel free to adjust the curtain. Before we get started, does anybody have any questions or concerns about the course, issues, sort of in logistics? I know that there are a few problems with some of the bits of hardware, and we'll work through those this morning without difficulty, I'm sure. So the roadmap for the course is that today we're going to work with some hardware, and the goal of this morning's session is to get you up and running with these little mobile robots and work through any bugs that you may have with them, and for you to build a system here. ROS short course, we're in module 3. We're going to get joystick control of these things with a joystick on your PC and the robot driving around, talking over Wi-Fi, and you'll be communicating via ROS topics. And then that's just sort of driving around. And then this afternoon, we're going to get deeper into RViz, and we're going to look at how in the demonstration that I gave yesterday, I fired up RViz, and you could see a little representation of the robot driving around in the RViz world, and it was clearly informed by the sensor values of the robot. You move the robot or tilt it around, and the representation of the robot does the same thing. So this afternoon, we're going to write a universal robot description format XML file, which specifies the kinematics of the robot. And then we're going to see how that fits into RViz and how you feed enough data into RViz in order to get it to actually animate and represent quantitatively the robot. And then the plan for tomorrow is a two-part plan. First is to look at Gazebo, which, unlike RViz, is not just a data visualization tool. It's actually a physics engine that does 2D physics simulations. And Gazebo originally started as part of ROS, but then spun off as its own separate project. And we'll take the ERDEF that you developed this afternoon, and you'll expand it into an SDF. And an SDF has not only the kinematics, which the ERDEF has, but it also has inertial properties and physical properties, friction, stiffness, and things like that the physics engine actually needs to simulate. And then the last module on Friday afternoon will be Gazebo simulation and integration with ROS. So you'll actually you'll take your simulated robot in the Gazebo world, which you had previously been driving around in the real world, and you'll drive it around in the simulator. And you'll see that if you go too fast or you turn too fast, the robot will tip over. It has real physics in it, and so that's the goal for the next 4 modules. Any questions on where we are on the roadmap? Okay. Then for today's module, module 3, this is the first time I used the EduMIP was this last spring in my robot systems programming class, and the class got very much happier after they had hardware in their hands. I think it's fair to say. Wouldn't you say that was the case, Ender? Yeah. Yeah. So I'm going to interface with joysticks. I want you to read about timer documentation, and I want you to read this tutorial about running ROS across multiple machines. And I'll briefly go over these in the first 45 minutes, or hopefully not much more than that hour. And I think most of you have assembled, so this is reading and some documentation to look at. The sensor messages that we're going to be using joy messages, geometry messages. Then we'll spend some time assembling your EduMIP, and the documentation on assembling your EduMIP is at this link. This link was broken and I just fixed it. Is on this page, which hopefully you've been looking at, and you'll be working on this node right here, node 4. I think most everybody has their EduMIP physically assembled. We had some problems with one of the downsides of an open source electronics, same for mechanical, project is that when vendors manufacture the open source design for production, and they're choosing contacts, they don't choose the gold-plated contacts that are really nice and it's going to last forever. They choose the tin-plated. They choose the cheapest stuff. And so the build quality on these things isn't very great, and we had one failed USB connector. I haven't had a huge number of failures, but I have had a few of them that were clearly just like, things falling off the board where the wave soldering didn't get done properly. And we do have a soldering iron here of Carl's that I'm going to steal and take home with me because it's a really nice weller. So if you need to do any soldering.
I think we also have a couple more parts around in the set.
Yeah, and I put one of my spare blues into service, and I got one more blue with me. So if your board has a part that fell off, then we've got a spare for you. Unplug. You're gonna build up the board, and then go through a test sequence where you bring up the board and then bring up ROS, and then once you've got ROS, the Linux and ROS running, then you can flip back to the main assignment. And the main assignment is going to be to drive the robot around with a joystick. And when you're doing that over Wi-Fi, then you're done. So that's a brief overview. John? Okay. So let me just dive into these things a little bit. Assignment number 2, assignment number 3. So a little bit about, that was a good suggestion about looking at the web pages earlier rather than later. Because for every package, for example, the joystick package, here, this is an example of documentation. We're going to click on Kinetic. This is a package that handles a bunch of joysticks. It's maintained by Jonathan Boren at jhu.edu, who's the ROS whisperer that I mentioned, and this is one of the more mundane packages that he maintains. The main joy that we're going to be using is a joy node, and it handles a lot of different joysticks. When you're diagnosing joysticks on Linux, what you want to do, first of all, is type dmessage to figure out when you plug in the joystick where it is. And the other thing you can do is, I like doing watch -n1 ls USB. So when I plug in the joystick, bang, you get an additional device that pops up and you can kind of see what's going on. And dmessage will tell you that the joystick is here, and that it's going to be input 0 in the joystick, and we can run a ROS node. There's a package called Joy, and here's the documentation. Joy is the published topics, and the type is sensor messages.joy. The default device is dev input JS0, and so we can make sure that we have that. Yep, there it is. And if I do a watch -n1 dev input JS0 and I unplug the joystick, then, sorry. No, it's too long stream, so that's not working. The joystick device entry will come and go depending on whether I have it plugged in. There's a couple of arguments, and so documentation on the package. Most packages contain a link to the GitHub and source. But we don't have to actually pull down the source. We could pull down the source by just cloning this repository into our catkin workspace source directory and do a catkin make, and it would work. But instead, you want to do sudo apt get install ROS kinetic joy. So ROS kinetic joy, and tab completion will show all the different alternative joy things. We just want the joy package. And so in my case, it's already installed. And then I'm going to run a ROS core here. And then I'm going to do, up here, I'm going to do ROS run. The joy package, and the node that I'm going to run is joy node, which is a Python node. And so it's publishing on the joy topic, and if I do ROS topic echo, going back here, joy node, so it's outputting a sensor messages joy type, and so we can look at that, and we can see that it's a header, and then it's an array of float32s and it's an array of int32s, which is the buttons. And so ROS topic echo / joy, and nothing happens because these joysticks only generate data when you actually move the stick, and so when you move the stick, then you get data, which actually can be useful because you know whether somebody's there or not. They're not great for deadman capability, so they don't tell you whether somebody's actually holding it, unless you actually make a deadman capability for holding down a button or things like that. That works for short periods of time. It doesn't work for more than a few minutes. And so we'd like to control our EduMIP with this thing, and the standard package that's provided that we don't have to worry about interfacing to it doesn't execute twist messages, and that's what our EduMIP wants in order to drive. It wants a sensor, it wants a geometry message twist, geometry message twist message in order to give it driving directions. And so the node that you're going to write is going to be a node which reads these joy messages by subscribing to the joy topic and publishing twist messages. And I've programmed the EduMIP that if it doesn't get a twist message in a few seconds, I don't remember what the timeout is, you can look at the source code, then it'll stop. So it won't just go AWOL, you know, off the end of the room and down the stairway. And so I've suggested that when you write your node, which subscribes to these things and publishes twists, that you use a timer so that it's publishing those messages at a regular rate. 10 hertz is a good rate for this kind of a thing because it's fast enough that it captures most of human response, and the robot's perfectly happy with 10 hertz. So back to the documentation. So timer documentation, we looked at this a little bit yesterday. You can read about timers. You can create delay timers, callback timers, all sorts of things. And there's also a little thing on ROS time, on making calls to ROS time to read the real-time clock. Read this documentation on running ROS across multiple machines. And what we're going to be doing is making a system that looks like this, where the joy node is running on your PC. It's publishing a joy topic. You're going to write this node, the EduMIP ROS joy node, subscribes to joy, publishes EduMIP command, which is a geometry message twist. It's a twist message, which is part of the geometry messages package. Color is a known bug in this version of RQT graph, so ignore it. It's been documented, and it's not going to be fixed in 16.0 in Kinetic. It's harmless, and this is the EduMIP ROS balanced ROS node, which is provided with the distribution. I do suggest that you do a get pull on that on the robot to get a few minor changes. And so all of this stuff is running on your PC. Wi-Fi is here, and all of this stuff is running on the robot. And not shown here yet, the robot's publishing its state as a EduMIP state message, which is a custom message at 5 hertz, but nobody's subscribing to it here, so it's not shown. So we want to run ROS across multiple machines, and so this is the tutorial that's go back, forward. So the suggested reading is running ROS across multiple machines, this link right here. And my guess is that some people have gotten to this and some people have probably not gotten to this, so I should probably review it. Is that correct? Okay. So I'm going to bring up my my bash RC. I usually put this stuff at the end of my bash RC. Let me get rid of some of this junk. So the two environment variables that you need to run ROS across multiple machines is that that every machine needs to know the URI of the ROS master, and so that's an IP name or an IP address. It could be localhost. Anything that your machine can resolve is fine, and then it has to specify a port number. By convention, 11311 is the port number, but you can use different ones. There's nothing sacred about that. And all the different machines that are sharing the same ROS master, and for the purpose of this course, we're going to stick with one ROS master. Their shells need to have the environment variable ROS master URI set to the same thing, and that machine needs to be running a ROS master. If you try to run a command on a machine that doesn't have the ROS master going, so like on this machine, I just killed the ROS master, ROS topic list, then you'll get an error that says unable to communicate with the ROS master, not surprisingly. And then when I do have a ROS master running on this machine, then you get ROS topic. So the first thing you want to check on machines when you set up the environment variables is remember to either kill the shell and restart it if you've edited your bash RC, or source your bash RC. Then look at the environment variables. So print and grep ROS, and you can see your environment variables. You can check your ROS master URI and your ROS IP. ROS IP is sometimes called ROS hostname, and those are equivalent. And you can put names or IP addresses in either of them. They're exactly equivalent. Notice just a brief aside. Working with folks yesterday, I think that there are a few folks who are new to Linux, and one of the things that's nice about the new bash shells is I don't like typing. My hands are arthritic, and so, for example, if I want to SSH into something, I will type Control R, and I'll do a backward search into my command history and SSH. That's the first SSH, and then I can do Control R again, and I can scroll through all the different recent SSHs that I want, and just select the ones that I want. And so, Control R allows you to search backwards in history, which is sort of a regular expression search of doing up and down arrow. So definitely save yourself effort and frustration if you don't like typing like me. The ROS IP or ROS hostname, like this is one that usually works. ROS hostname minus I. ROS hostname minus what is minus A gives you the IP address And that works great as long as your machine has a single IP address. Oftentimes you'll have a machine with multiple NICs, and it has multiple IP addresses on the multiple NICs, and then you can get sort of craziness. So ROS IP wants to be the host name of the local PC, and so on my PC, I'm going to be running the ROS master, and I'm going to be running ROS packages here, so those two IP addresses are the same. On this one, the ROS master URI is going to be 10.101, and the ROS IP is going to be 10.102, which is the IP address of this thing. And I have a label maker, by the way, over here. And if you want to give Andrew or me the MAC address of your wireless card for your EduMIP and the MAC address for your wireless card here, we can give you a static lease on the IP address, so you don't have to discover them each time you hook up. And then you can make a label, which is very nice. So this just walks you through the process of setting up the environment variables, ROS master URI and ROS IP, and so it's pretty straightforward. Documentation on sensor message, geometry twist message. I mentioned yesterday that there's a fairly rich set of sensor messages. Here are all the sensor messages that are the baseline sensor messages in the sensor messages package. For example, navsat fix is a simple GPS fix. There's an extended fix message which has all the additional things that you get with ephemeris and things like that. But these messages are often a good place to start. And geometry messages are a bunch of standard messages that do a lot of things that you'd want to. They provide the basic functionality to encode lots of kinematic stuff, both positions, points, lines, planes, twists, time derivatives of spatial transformations, things like that. And common message types. And you can also, if you go to this web page, common message types, you can drill down into, these are all the basic common message types: action live messages, diagnostic messages, geometry, nav, and sensor messages. These last three are the ones that you'll probably spend most of your time. But when you're writing your own code, you would be well advised to follow the design pattern of use a geometry message, use a standard message if you can, and if the standard message is broken, consider encapsulating it, because that way you can sort of cooperate and make use of, in an easy fashion, a lot of existing software. Questions? All right, setting up the EduMIP. I think the joystick assignment here is self-explanatory. I will demonstrate it, but you want to zoom to this web page that I made here that I think you've all been working from, and I've been slowly correcting the bugs in the web page, and I'd be grateful if you tell me about additional bugs. And I think most folks are done doing assembly. We have some spare wires and things like that if you need them. The motor wires are particularly fragile, and the test sequence is basically to your BeagleBone black wireless. This should say blue here. That's a typo. Comes with an image on its internal 4 gigabyte flash with a Debian image. So the first thing to do is just power it on and plug it into your PC with a USB cable. USB cable. And see if it comes up. Has everybody figured out the Ethernet over USB thing that's going on with these? Any questions about that? Yes? Okay, all right, we'll do a quick demo. It's easy. So I'm going to power on my EduMIP, and I've got a micro SD card, so it's going to boot from the micro SD card, but the principle is the same. I recommend with these things, you don't need to have the antennas pointed up all the time. I sort of fold mine down. number one. And number two is it's a good idea to power off the Linux before you unplug the battery. It's a good idea to unplug the battery before you put the thing in your backpack, just so that your keys or whatever else are not going to short out on hot traces on the board. So when traveling, I recommend you unplug the lithium polymer battery. You can power down either by logging onto the system and typing sudo power off, or the power button right here. If you hit the power button, it'll do a power off, and it'll stop flashing, and there'll be one vestigial LED, and then you can pull the battery connection, and the thing's really cold. So when it comes up, Jeff made a really nice image here, and thank you, Jeff. And the default Ubuntu image didn't have any Ethernet connectivity over these existing ports, and so you had to sort of connect through it through a backdoor, a serial port, or through a USB Ethernet. And Jeff has configured it so that it's actually very easy to connect to. The two ways that you can connect to it are, it's actually acting as an access point, and so you can connect to it, and each BeagleBone comes up with its own, so you see all these BeagleBones are running in the room, and they're all advertising as access points. And so one way to connect in is, I know that mine, because I checked, is BeagleBone 5E04, and so it should be here in the list somewhere. Yeah, right here. Okay, so here's mine. And so one way that I can connect to the BeagleBone is connecting through its access point, 5E04. The password for the SSID, and this is on this web page further down, is BeagleBone with the B's capitalized and everything else lowercase. So one way to connect is to connect in wirelessly, and the password is BeagleBone. And yes, connect. And when we do ifconfig, we'll see that my wireless Ethernet adapter, and for those of you who are new to this, I think not many, this is my my hardwired Ethernet adapter right here. This device, it's a physical device. This is a virtual device, which is the loopback Ethernet device, and this is my wireless Ethernet adapter. And it's DHCP'd to 192.168.8.116. And so if you see your wireless going to a .8, that means that it's connected to the wireless access point here. And by convention, the Ethernet address of the BeagleBone itself is going to be always .1 on whatever subnet. And so I can do SSH 192.168. So I'm doing SSH Ubuntu at 192.168.8.1. Password is temp. And this is nice, but it also kind of sucks because I can't get to the outside world. So I ping www.hui.edu. It doesn't know hui.edu because we're just connected between these two, and we're not connected to the outside world. So better, the preferred arrangement is if you connect through to the access point. So I'm going to log out of there. The more common way to connect with these things is to use a USB and plug into the USB port on the top of the machine, right between the rabbit ears. The USB port, we're finding that the solder is fragile, so be careful. And if I type ifconfig, nothing happens for a period of time, but then pretty soon something will happen. So this is designed to serve Ethernet over the USB port as a DHCP master. And there we go. And so these two new virtual devices that appeared, 192.168.7, so this means that my PC has the Ethernet address 192.168.7.1 over this USB port. It also has the Ethernet address .6.1 over this Ethernet port, and it's still connected wirelessly to the access point over this. And the BeagleBone under these things has a .2 address. So if I want to connect in SSH. So if I connect through to the .7 subnet, the BeagleBone is .2, and there it is. Password is temp password. And I think the USB is probably the more common way that people will connect through to it, but it still suffers from the problem that I can't pull anything from a repository. I can't access the internet. So better that you enable the Wi-Fi. And in the Debian image that I built for my class last spring, I had it configured so that once you configured the Wi-Fi once, it would automatically reconnect. And I haven't had enough time. Something didn't work with that same method that I used, and I haven't had a chance to debug it. So if anybody has any spare time and wants to fix Conman so that it automatically reconnects when it boots up to the Wi-Fi base station, that'd be great. I don't think it's hard. I just didn't have enough time to get it working properly. The cheat sheet for connecting through with Wi-Fi is more etc network, bless you, interfaces. And in the tail end of the network interfaces file, this is the cheat sheet for Conman. So Connection Manager CTL is a little interactive thing. And if you follow these things, if you follow the sequence of commands exactly, you'll be able to connect through to the Wi-Fi base, the Turtleman. So Conman CTL. Tether Wi-Fi off is actually not necessary because we disabled that in the image, so you can skip that. And you can type help and see there's a whole bunch of messages here, commands that you can do. So I can skip over Tether Wi-Fi off because I did modify the configuration file so that it's always on, that it's not on Tether. So enable Wi-Fi, scan Wi-Fi, scans the available networks, tells you when it's done, services, and these are all the Wi-Fi access points that are available. And when you want to connect to one, we need to turn on the connection agent, so agent on. And I've already connected, but if I wanted to connect to, this star means that I've already connected, and when I enabled Wi-Fi, it actually connected at that point some seconds ago. But if I hadn't connected previously, I'd say connect, and I'd choose, I need to give this as the argument, but it does tab completion. So I'm going to connect to Wi-Fi 7.4, tab completion, that's the whole thing, you don't have to type it. I'm already connected, but I'll go through the process again. So it's already connected, so it gave me an error. It would ask for the Wi-Fi password, which is turtlebot, lowercase 707, no space. And that's it. Once it'll think about it for a second, and then it'll say connected, and then you're done. And the configuration file is in etc conman ctl. I think it is. Yeah, etc conman main.conf is the configuration file, and that's the configuration file that I created that worked on the Debian image just fine this spring. But obviously I got something wrong because it's not automatically reconnection. But I think that's where the action is. So if anybody wants to fix that, that'd be great. Anyway, so now we can ping hui.edu. Jeff very nicely created a Catkin workspace. There's a bin directory that you can use if you want to put executables. The Robotics Cape installer is there. And let's see, Jeff, what other things we want to mention? The driver for the Wi-Fi.
Yeah. Let's see if I can figure out
I'll tell you, why don't we put that up on the web page? So the driver, Jeff had to provide an updated driver for the Wi-Fi, which is in your image. But if you do a sudo apt-get update and it updates that image, then you're going to lose your Wi-Fi. And so what we'll do is we'll modify the web page with a link to where you can get that binary.
Well, sudo apt update is okay.
Upgrade. Okay, so nobody's going to upgrade.
Nobody's gonna upgrade.
All right, we're fine. I misunderstood you.
Yeah. No,
Okay.
you might upgrade. Remember, update is just creating the package.
Oh, right, I'm sorry.
Upgrade.
Yeah.
And
Oh, you're right.
Disk upgrade.
Yeah. So yeah, we will. People will upgrade. So.
But who knows the upgrade? At some point, the upgrade can fix it.
Right.
Right now.
Okay. We'll add to the web page. So there's going to be a link to the binary file, which is the driver, and where you can drop it into your file system with sudo if you suddenly lose Wi-Fi. So I'm connected here, and Catkin workspace, source, Catkin workspace. And you'll need to do the usual thing with SSH keys if you want to work with your own repos. So everything works normally here. This is an Ubuntu distribution, and the if you use the Debian image on this thing, then you need to do a source build a ROS, which is just a little bit tedious. It takes a day, and then doing software updates is harder. And we've configured this with swap file. It's the EduMIP has half a gig of RAM, and we've configured it with a 1 GB swap file. We forgot to disable Apache automatically to disable launching Apache. So Apache is launched by default. It's not using much memory or CPU, so it's not really harmful. But you can kill that if you want. You need to sudo kill the process ID, or you can disable the process launch in the boot sequence. And DNS mask, this is the thing that's doing DHCP over the USBs. And you notice that if I do print environment ROS, I have my ROS master URI set to this PC, and I have my ROS IP set to the IP of that PC, all on the Turtlebot Wi-Fi network. IP config. IF config. We can see that on the wireless network, I'm now 192.168.10.102. That's this address, and I label them because I can never remember. And it's also serving Ethernet on these two USB connections. And this one up here is the Ethernet connection where it's simultaneously connected to the Wi-Fi base as a client, but it's also serving Wi-Fi as an access point over the same access point through this virtual adapter. And IWconfig tells you a little bit more about the wireless connection. That if you want to know which thing you're hooked into, your 802.11, Turtlebot 2.4, connection rate, so on and so forth. And I think that this access point, it's a gigabit access point, should be fine for what our class is doing. I don't think we'll stress it at all. Back on my PC is on the left. If I type over here, if I on my BeagleBone, if I say ROS topic list, the most common errors that you see are just getting the environment variables not right. But if I have a ROS core running on this machine, then hang on a second. So I'm still connected to the BeagleBone wireless network. I need to connect to TurtleBot. All right, so I was still connected to this as the access point. And now if I do ifconfig, I have the address the actual address of my PC, which is 10.101, agrees with my environment variables, which says my PC should be 10.101, 192.168. And so ROS core appropriately was complaining. So we've got a ROS core running, and I can say ROS topic list. And of course, in the exercises that you've already done, you've seen that you can actually publish from the command line if you want to test things out. But as long as you can ROS topic list on both machines, that means that you're good. And so there's sort of a step-by-step thing here for that's the ROS. You're also going to, I guess I jumped ahead of myself. Before you get to the ROS point, you're going to test the BeagleBone by booting it up in an image, connecting to it probably with the USB, and the things that you want to test on your BeagleBone is there's a bunch of RC commands that are built in RC, a whole bunch of RC commands right there. They're all in user bin, and they access the actual hardware of the robot. Now, we as users can't normally access hardware directly because we're running in virtual machines. And remember the design pattern in Linux, for example, if I look at ls-l RC check battery user bin, RC check battery. You'll see that it's owned by root. Everything in user bin is owned by root and the root group, and yet it's acting when I execute this command. It is as though I have super user or root privileges because I'm directly accessing the hardware, which is not in a virtual machine. The reason I can do that is the design pattern in Linux is that this S bit is called a sticky bit, and when you set that with chmod plus S file name, so if you want to, then the convention in Linux is that when the sticky bit is set, then any user can execute this executable, but the executable runs as though root were running it with root privileges, even though you as the user do not have root privileges. We only have execute privileges because you can see you have X's here, so anybody can execute this executable. And so this is the way the Linux has, the Linux designers have handled the security. And it's really great because for those of you who have programmed in Windows, which I have done only a little and it's been really awful, you have to get these like certificates. And the certificates, you need to like carry them around and they have .NET stuff. It's really completely unknowable. And this is like super knowable. So the shell script that I sent around, when you compile your own EduMIP ROS balance program, I provided a shell script, catkin workspace source EduMIP ROS balance, EduMIP balance ROS in the scripts directory. And the script that I provided, you can type the commands, but these are the two commands you need: is sudo change owner to root the executable, and this is the executable that's created for EduMIP balance ROS when you do catkin make, and then you need to set the sticky bit, and that's sudo chmod plus S, and you need to do them in this order. And I typed that a few times, and I don't like typing, and so I just made this little script.
When you do a get pull, before you do a get pull, you have to undo those on that EduMIP balance ROS repository?
Nope, because these are compilation products that are in the ephemeral directories devel, right? Yeah, so so it has no effect on your source directory. So remember, the build and devel directories are entirely ephemeral. You can blow them away. So getting back to this, in testing, you want to just run through these tests, and you need to calibrate, at a minimum, you need to calibrate the gyros. And and you can optionally calibrate the magnetometer and test the magnetometers. We don't actually using the Maggie, but if you don't calibrate the Maggie, then you'll get a warning every time you use the IMU. And so if we want to do RC test encoders, and then just rotate the wheels, yeehaw, E2 and E3 are the encoders, and RT test servos. If you give it a duty cycle, you can type this to get the help message. So all channels, duty cycle of 0 is 50% minus D. Is it D? C, frequency, position. No. Oh. Test motors is what I want. Test servos is for the RC servos. So RC test motors minus D. I thought it was minus D. That's 50% duty cycle, so the wheels are not spinning. And don't worry about this error. That's just a bug in this version of the roboticscape. Ignore it. 0.1 duty cycle, we get slow rotation in one direction. And minus 1, we get fast rotation in the other direction. If anybody wants to fool around with RC servos, you can drive up to 8 of them. I brought a half dozen or so in my kit. And if anybody wants some these connectors for connecting serial and other devices, I brought a whole kit of connectors. So if you want, I can dole out some connectors if you've got a project in mind. I did bring a GPS, which is already connectorized for this, which I've never tried. So if somebody wants to try out the GPS with the GPS monitor ROS package, you can do that. So since I'm connected with Wi-Fi, I can disconnect my USB. So you want to test the motors, calibrate the gyros, which involves sitting in place, test the gyros. Mainly you want to see when you test the gyros that the angular velocities are near 0. That's the important thing, and the gravity vector looks sort of rational. Calibrate magnetometers, you need to rotate it around so it calibrates the bias in the magnetometer. And when you test the magnetometer, the magnetic field strength in Baltimore and here is within a few percent. So the total field vector should be on the order of 50 to 60 microteslas. And then last but not least, you can see that everything's working, running the standard RC So my session hung up. By the way, for those who are not terribly familiar with SSHing, if you're stuck if your remote session is hung for some reason, and you want to kill it and get back to your PC, you hit carriage return to start a new line, and then type tilde ... and that'll kill the remote session. So the SSH is looking for tilde period as the first 2 characters of a new line as the escape character to bring you back into the foreground. That's when I disconnected, so it's 10.102. So I should have logged out and logged back in over Wi-Fi. That's why when I disconnected, it went dead, and I unplugged my USB. Let's see, where was I? RC, yeah, and then RC balance. Is the test of the program. And so this is not a ROS version of the balance program. This is just a version of the program that Tom Bewley and his student Strawson designed. And so these different angles are the tilt angle of the body and the tilt reference, and the heading angle of the body and the heading reference. And this is the battery voltage. A fully charged battery is about 8 1/4 volts. It's 2 packs that are stacked on top of each other. And so this is not a ROSified program, and you have the source code for the EduMIP balanced ROS program. And so I took that and I pulled out all of the standard I/O and turned it into ROS information messages, and have it subscribe to a twist message and publish a EduMIP state message. And when you kill it, it falls down. We have extra screws if you are missing any screws of appropriate length. And then instructions here are pretty straightforward for testing the EduMIP balance ROS program. The only wrinkle is you need to change the ownership and sticky bit for the executable. And I urge you to go to Catkin Workspace source, EduMIP balanced ROS, and get pull. When you do a get pull, you'll probably get an error message because it says that the EduMIP ROS balance .c++ program has been modified, and so you can just rm source EduMIP ROS balance.cpp, and then you can do a get pull, and the conflict will be resolved. And let me think. Notice that there aren't any message files here. It's a common design pattern that if you have a bunch of packages that are going to be using common messages, you usually make a message package. So EduMIP messages is such a package. It doesn't have any source code. All it has is some message definitions. And right now it just has one message definition, which is EduMIP state. And so the EduMIP state message contains a bunch of float 32s for these are the things that we saw. These are all the variables that we saw in the EduMIP, in the RC balance program that were being printed out on the screen. And in addition, I added a little odometry, so the wheel angle left, wheel angle right, body frame easting, northing, and heading. And this is not actually using the magnetometer. This assumes that the vehicle is pointed north when you turn it on. And so it's fake northing and fake easting. If anybody wants to modify this to actually use the magnetometer, that would be great. And it also reports the battery voltage, whether the balance program is running, and whether the controllers are active armed. And when the battery gets much down below about 8 volts, when the 2 battery packs get below about 8 volts, which usually takes a minimum of 3 or 4 hours, that's when they're exhausted. And you can see RC, check, battery. So I just had this thing plugged in all night, so it's pretty much a full charge, and you can see that you can monitor the jack voltage as well as cell voltage. So that's pretty much it for setting things up. There's additional notes here on various topics, and then and this is the actual thing that I want you to do. I do think that it's valuable to go through this process of bringing up a machine from that's not just a pre-built desktop, to go through the process of connecting through an embedded system. You can test your joystick with jstest.gtk. You'll have to install it, and then do this tutorial on Linux-supported joysticks, and write a program that looks something like this. CD ROS Catkin Workspace, source. And I've asked you to create a package called EduMIP ROS Joy. There it is. It's a simple package. All it has is a launch file and a source file. And so my file looks like this. Let's see, that's a little hard to see, isn't it? Is that one better? Can everybody see that? So my package works like this. The main will start down here. Does ROS init, creates a node handle, and it advertises. It creates a publisher. So we're going to node.advertise. I love the terminology. It's kind of hokey. It creates a publisher object, and which is a geometry, which is going to publish a twist geometry message, and it's going to publish it on the EduMIP command topic. Now, right here, I've sort of dirtballed namespacing. What would normally use if you're doing namespacing pretty carefully is you just publish on command, and in the launch file you would namespace into the name of the robot, like EduMIP1 or EduMIP2. But I wanted to be able to, I created this for my course so that I didn't have to teach namespacing before the basics. And then you want to create a subscriber, which is going to subscribe to the topic joy. And it's going to, every time a joy message is published, it's going to, then it receives one, it's going to publish it's going to execute the joy callback message, and the queue size is 10. Then I'm going to create a timer that's going to tick off at a 100 millisecond interval, and it's going to call the function timer callback, and then I'm going to block on ROS spin. All these things responding to the timer and responding to the joystick message take a very short period of time, microseconds. If I had something that was substantial computation and I didn't want to block the processing of callbacks, because callbacks are called sequentially, only one is executed at a time, which is why you don't need to worry about mutexes for sharing common data in callbacks. If I had something that was going to take a minute to execute, I wouldn't want to do it in a callback. I would launch a boost thread separately to do that computation on the side, so the callbacks could be serviced simultaneously. And boost is part of ROS, and so all you need to do is make the package depend on boost, and you can use everything in boost. And if anybody is unfamiliar with boost threads, I can give you an example package to show you how to do that. So the timer callback, let's start here. There's two callbacks. The joy callback is, and I'm committing a sin here, but it's for good reason. I wanted these examples to be simple, and so I didn't want to obscure them with several pages of class definitions in public and private. So this is sort of C-style coding, and I've committed the sin of having global variables here. So I will confess to that. But the reason that I committed that sin is that I wanted the program to be one page, and to focus on the ROS stuff. And I think that most of you are good enough C++ programmers that you understand the sin and you know how to atone for the sin with a proper object class. So I'll let you do that. And there's plenty of examples online. So this is the simplest possible bare bones program. We're going to create a twist message as a global variable, and the command velocity publisher was declared here, and we initialized it down in the main. So we actually initialized that value down in main, down here. That's where it got initialized. So every time a joystick message comes in, I'm going to save the first joystick axis in the command velocity twist.linear.x variable, and the 0th joy axis in the command velocity twist.z message. And so the joystick can publish as many messages as it wants, and all it does is populate the x, the linear x and angular z degrees of freedom. And then 10 times a second, this thing gets called, and it publishes the twist on the EduMIP command topic. And so when we run this, so this is what's going on my PC, and this is what's going on my EduMIP. So so what do I need going on my PC? I need a ROS core. So we've got a ROS core, ROS topic list. Takes a minute for the first time. So we've got ROS core is going on both machines. That's my EduMIP, that's my PC. And I'm going to run, see, ROS launch, EduMIP. Tab completion is a little bit slow on the ARM. Balance ROS. That's the name of the package. And the name of the node is the same thing. There we go. So I'm going to run EduMIP balance ROS.launch. And you can take a look at that file. And so we can balance. And on my PC, I can do ROS topic list. And so we've got EduMIP command and EduMIP state. It's publishing on EduMIP state. And so there's the state messages streaming up at 5 hertz. And then this is my package, ROS launch EduMIP my robot. There's a couple different examples here. So this one, this first launch file is called EduMIP ROS Joy, and it launches a joystick package, the Joy node from the Joy package, and it gives it a name Joy node. And then it launches from the EduMIP ROS Joy package that I wrote a EduMIP ROS Joy node with the same name. And that's fine if you want to run one joystick. If you want to run more than one joystick, they need to have different names. And so the package joy anon.launch. This launches a just a joystick package, and this is the syntax in the launch file. If you want the if you want ROS to figure out a random name for your node, so you can run multiple instances of it. So it's the syntax is $anon joy node, and so it'll riff on joy node and add some unique characters to that. So we're going to just run EduMIP ROS Joy, EduMIP ROS Joy.launch. So it's unhappy because my joystick's not plugged in, which is true, so I'll kill it. And I ran, in this instance, to do this demonstration, I ran a persistent ROS core because I knew that there would be some mistakes and I would want to bring the nodes up and down. And I didn't want to necessarily be bringing a ROS core up and down each time, because once the robot connects to ROS core, if ROS core goes away, then I've got to start that stuff all back up again. So we're in business. And I can say ROS topic list and ROS topic echo. We saw the joy messages, which only happened when we moved the joystick. now these messages are being transmitted at 10 hertz, whether or not I displace the joystick or not, just because that's how I wrote the program. And now we can see the EduMIP state messages streaming up, and they have real odometry on them and heading. If you press there's a little mode button. One of the buttons is labeled mode. This comes up in sort of beginner mode, and if you press the mode button, then on this screen you'll see it switch to advanced mode, and it's kind of like on the El Cheapo economy car that I have, where it's got the like sport mode. I don't think it actually does anything, but it makes you feel like maybe it does, and last but not least, RQT graph. So this is what's going on. Joy node, joystick. This is a little piece of code you're going to write. Publishing EduMIP command. This is Ethernet over here, wireless Ethernet. Balance program, publishing state, and my ROS topic is subscribing to the state. Any questions? Bon appetit. Andrew and I are available to help with anything. Oop. They're pretty rugged.
When you get into C++, it's like real